Hello, we are AI researchers from Kalian, and today I'm excited to present our work, GeoAvatar, developed together with Professor Kyung-Moon Park from Korea National University. In this talk, I will introduce our motivation, explain our method, and finally show you how it achieves state-of-the-art performance for 3D head avatar generation. First, let me briefly introduce 3D Gaussian splatting. Instead of relying on volumetric grids or implicit functions like NIRF, this approach represents each 3D point as an anisotropic Gaussian with color and opacity. It enables real-time rendering with high-quality results. Next, we use the flame model, a statistical 3D morphable model for human faces. It represents facial shape, expressions, and pose with low-dimensional parameters, providing a controllable way to generate 3D heads. However, we observe two important issues. First, the Gaussian distributions vary a lot across regions like the scalp, ears, or hair, where flame fails to capture geometry. Second, recent methods often modify meshes novelly, for example, by connecting lip vertices or oversimplifying teeth structures. This mismatch between flame and the ground truth geometry leads to poor mouth animation and artifacts. To address these problems, we propose two strategies. First, adaptive pre-allocation, or APS, segments the face into rigid, flexible, and mouth regions in an unsupervised way. Second, we modify the mouth interior structure. Inspired by Gaussian avatars, we extend the teeth model to include molars, the palate, and the floor of the mouth. This greatly improves animation quality. Still, 3D tracking struggles with subtle mouth movements. So we introduce part-wise deformation. We separately deform the upper part, like the upper teeth and palate, and the lower part, like the lower teeth and floor. This preserves relative structure while capturing fine-grained dynamics. To ensure consistency between the mesh and Gaussians, we introduce angular regularization losses. Combined with rendering loss, our final objective ensures robust alignment and stable Gaussian animations. Here's an overview of our entire method. We evaluate our model on benchmarks such as INSTA, NHA, ImAvatar, and NIRFace. Compared with baselines like Flash Avatar and Gaussian avatars, our method produces consistently sharper and more realistic results, especially in expressive scenarios like talking or laughing. Quantitatively, we outperform baselines on MSE, PSNR, SSIM, and LPIPS. Even with single-view inputs, our model effectively reduces artifacts inside the mouth, while Gaussian avatars still struggle, even with multi-view data. This shows the robustness of our approach. We also performed extensive ablations. Adding our components step by step shows clear improvements, and removing them degrades performance. This confirms that each contribution is critical to the final results. To conclude, our contributions are a novel segmentation of rigid and flexible regions, a modified mouth structure and part-wise deformation, a new angular regularization strategy, release of the dynamic face dataset, and state-of-the-art performance across multiple benchmarks. Thank you for your attention.